Okay. So we're continuing the first law of thermodynamics. And now we're into heat transactions. This kind of doing bookkeeping with heat, keeping track of it. So what could this heat do? Oh, a few words on the exam. You got the exams back. Adriana, congratulations. Okay. So don't worry, it's your first exam. If you didn't do as well on it as you thought you would, it gives you some feedback as to what to expect on the exams, the format of them. They'll all be very similar, and we'll try to have as many exams as possible. There was a good question about, are we going to have a review day before every exam? I kind of go back and forth on it, but right now, as long as they're useful, we'll do that. But once we start wasting time, then I'll say, and then it's my job to say no, right? But as long as they remain useful, it sounds good to me. Okay. So du, I'm not supposed to say du. I'm supposed to say what? Change in internal energy. So the changes in internal energy could be, now, I can even be more descriptive. What type of change? Is it very, very small because it's a little d? So you can say very small changes in internal energy or infinitesimal changes in internal energy. They can come from infinitesimal changes in Q, which everybody is heat. Heat coming or going. Infinitesimal changes in work. Okay, now there's a bunch of equations. There's a bunch of different formats of work. There was electrical work. There was the only type of work that we're going to be interested in, and the only hint you have at this, Alice, is that we have equations for it, is what type of work? What's that? I can't hear you. Mechanical? No. Mechanical's moving stuff. No. We have equations for it. W is minus px delta v. W is minus nRT, natural log v final or v initial. It's all what? Work to do what? Expansion of a gas or compression of a gas. So the gas can do work on the surroundings, or the surroundings can do work on the gas. That's the only equations that we're messing with for work. Now there are other types of work. That's this other dW, infinitesimal changes in other types of work. Electrical work. Alice's mechanical work. There's other types of work, but I think this is really all we're interested in, where our W is compression expansion work. Bomb calorimeter. Okay, so how do we go from here to here? First, the little infinitesimal d disappeared and it turned into a delta. That probably means what, Kathleen? What does that mean? You went from a little infinitesimal d to a delta, right in front of the u? A bigger change. Or you could have done what mathematically? Integrated, right? Add up all those infinitesimal changes to get to the final state. And if it's a state function, heck, you didn't even have to integrate. You just had to take what minus what? Final minus initial, right? But that's okay. Right? If it's a state function, it doesn't depend on the path. It's just final minus initial. But they say delta U equals Q with little v. Now, little v probably means what? Volume. So that means, and it's a bomb calorimeter. So you're doing some reactions, and you're keeping what constant? Oh my gosh, this thing weighs a ton. You're keeping what constant? The volume, right? So why would this be called a bomb then? Yeah, if it's a exothermic or endothermic reaction, heat will be changing, but gases pressure. I mean, gases. Can the volume change in a bomb calorimeter? No. So if it's a gaseous reaction producing gases, which most of them are, right, and giving off all this heat, exothermic, huge amount of pressure. So it's literally a bomb. It's literally a bomb. That's why the thing weighs a ton. It's all nice and sealed up and everything. Right. Ooh. Okay. So QV, little v means constant volume. So do you see how they went from that equation to delta E equals QV? What happened to the W? What happened to little infinitesimal dW? Why isn't it there? Because volume can't change. That means can you do compassionate compression work, or no, you can't do a PV work because the volume has to change. So that's why it's gone. That's why the internal energy is just the heat transfer. Okay. Q equals C delta T. C is the calorimeter constant. You remember doing that kind of thing? I think we did it once in general chemistry for sure, where you had to measure the calorimeter constant. What are its units? Watch out. Q has to equal C delta T. That's the hint I'm giving you. C has to be in units of what units? It could be joules or it could be calories. It has to be an energy unit all over Kelvin or Celsius. You pick it, right? It's whatever you define it to be. But it's a constant, or you're assuming it's a constant, right? You're assuming that heat capacity. Now, what is heat capacity? Right? What is the heat capacity of this? Literally, what is it? Depends on what it's made of. It's the amount of energy it takes to raise the temperature of this thing 1 degree Celsius, 1 degree Kelvin, right? So is that heat capacity going to be the same under different temperature conditions, you think? It takes so much energy to raise the temperature of this thing 1 degree. What if this thing, it's steel, what if this thing was 1,000 degrees Celsius? Would its heat capacity be the same? I don't know. Someone knows. You look in tables. You Google it, right? But odds are no. These heat capacities change with temperature. Okay, so you're assuming, isn't there a problem here then? Aren't we assuming that if we're going to use that value for heat capacity, we're assuming it's constant over temperature, aren't we? Because look at that temperature range, delta T. You're assuming that heat capacity is constant over that temperature range. You're pulling it out of that integral, right? It may not be the case. In fact, you're going to see a lot of plots. It's not the case. Life is a lot more complicated than that. Sandy, is the calorimeter constant a heat capacity? What is heat capacity? We did this in general chemistry for sure. Physics, you did it. What's heat capacity? Give you a hint. You also had specific heat. They all dealt with these problems of heat transfer. Or how much energy is it going to take? Or how much energy is going to be given off if this object goes from this temperature to this temperature? And those are the questions you answered. And to answer it, depends on what, like Juan was saying, depends on the type of material it is. We're going to find out even depends on the temperature of the system, but you look it up for different things. It was just specific heat was heat capacity per gram or heat capacity per mole. It was specific to the amount. Heat capacity or calorimeter constant, same thing. You take the entire object, how much energy does it take to raise it 1 degree? It's not per gram, per mole of heat capacity or substance, no. All right? So water has a heat capacity, so many joules per degree Celsius. Water also has a specific heat, 4.184 joules per gram degree Celsius. you get the same answer out of both of those. Okay, except if it's specific heat, you know, it has to be this body of water. They have to tell you what it is. Okay. Molar heat capacity at constant volume. So that little m must mean molar. Yeah, must mean molar. Okay. Notice that little v down there. Constant volume. So heat capacity, what it really is how the internal energy is changing with respect to temperature. And if you keep the volume constant, well, then that's the heat capacity at constant volume. Okay. So if they're trying to say that's this plot here, right? It's a slope. How is, all right? Plot internal energy versus temperature. That's what they did. And you measure the instantaneous slope. That's what it is. And they're partials because, man, there's more variables than just temperature. That's okay. Let's keep volume constant. Can't change. Changing temperature. What's the change? How does the internal energy change? It's a slope. Does it look like that slope is changing in figure 211? Juan? Yeah. So is the molar heat capacity at constant volume changing with temperature? Yeah, most definitely. Okay. So when we do if we do, I'm not even sure what we're going to do there, but if we did this lab, you know, you're going to hope, I hope Smith says the heat capacity is constant over temperature. Otherwise, look what you're going to have to do. Right? Oh, we're going to get to it. It's coming up. Okay. It's actually a three-dimensional surface is what's going on. Okay. How'd they go from here to there? Something we're going to have to just get used to doing. They moved that little partial t up there with the heat capacity, constant volume. And they just replaced the partials with differentials. They're just setting up so you can do an integral. So you actually get some numbers for stuff, right? And if you get the numbers for stuff, you're going to get the area under the curve. You're going to get some values, some numbers, instead of just looking at instantaneous slopes. Okay. So that's all we're really setting up. And they said that infinitesimal change in U is CV dt, and that's just QV. Well, where's that coming from? Remember, heat capacity is, all right, the energy over the temperature. So if you multiply energy over temperature, temperature cancels. These are just infinitesimal changes. Okay. So they're just playing around with stuff a little bit. Enthalpy. Enthalpy. Enthalpy is internal energy plus pressure times volume. Change in enthalpy is Q sub P. You said this a few times in general chemistry, but I don't know if you caught on. What does that mean? Enthalpy is really what? Yeah, heat transfer, but under what conditions? Has to be constant pressure, which is the lab. It's perfect, right? Because we're under, well, not exactly 1 atmosphere, but it's a constant pressure. So it works great. That's why enthalpy is so common, and you hear about it a lot in a lot of courses. The enthalpy of this reaction is, well, yeah, because it's heat transfer under constant pressure conditions. Okay. Let's see, make sure I don't skip anything here. Okay. I don't think so. So, oh, here it is, right? Now we're here. So the heat capacity under constant pressures, how the enthalpy changes with respect to temperature. And how does the enthalpy change? Well, it's Cp delta T, how do you get it, or it's Qp. And what's coming up, I bet you, is that, yeah, it is. Do you remember we did this in our concept preview? Let me set it up for you. Okay, we've got, so that means, right, what did I do? I brought the dt over. Everyone following so far? Okay, well we want to get a number for enthalpy, so you have to integrate. Right? Make sense so far? Does heat capacity change with temperature? If it doesn't, you can pull it out of the integral. But if it does, well, here's an equation, right? With little a, b, and c. Little a, b, and c are what factors? I call them that anyway. Fudge factors, so you get the right answer. Otherwise, it's going to be a much uglier relationship. So we really got to put that in. Depending on what the compound is, here they're listed. Depending on what the compound is, you plug in the right a, b, and c. But the point is, and it changes with temperature. Nice. Realistic. You got to put it in for that. Then you got to integrate it. We did that in the concept preview. We found the integral of a plus bt c over t squared d quantity dt. We found that. Yep. Okay. I don't know if you believe me. We did. Okay. So we kind of made a transition here of, okay, let's keep volume constant, calorimeter. Now we're talking about enthalpy. Let's keep pressure constant, laboratory, right? What's going on in reactions on the bench. Reactions in a vessel that you let volume change on. Okay. That's really about all I have. A lot of tables they may only give you one, the molar heat capacity at constant pressure. Well, you can calculate the molar heat capacity at constant volume, the relation with the gas constant. Okay. So the homework only gives you one. You can get the other one if you need it. So that's a brief overgoing of what you read about. Any questions on that before we jump into the homework? I think we're ready for the homework. A sample consisting of 1 mole of argon is expanded isothermally at 0 degrees Celsius from 22.4 liters to 44.8 liters. Reversibly against a constant external pressure equal to the final pressure of the gas, and then freely against 0 external pressure. For the 3 processes, find Q, W, delta U, and delta H. Okay. All right, let's see if we can get started here. Probably start writing stuff down. Because sometimes if you write stuff down, it helps you recognize where to go. Now, instead of writing 1 mole of argon, I don't know if I'm going to need, I don't know what equation I'm going to need, right? We're just reading this question. But what variable could we write down for 1 mole of argon? Because it might give you some hints on what to do. What have you seen? What amount of a gas? It's in moles. Little n. Do we use little n for number of moles? I don't know if you're going to need it, but it might be a little guiding thing if you're totally lost, have no clue what to do. Okay. Expanded isothermally. Isothermally. Expansion. I don't know if it helps you to write stuff out like this. It might, but 0 degrees Celsius. Right. From 22.4 liters, So maybe call it, I don't know, V1 to 44.8 liters. Okay. Now we're supposed to go reversibly first. This is reversible. All right. Now, Robert mentioned something. I don't know if you can hear him mumbling up here. But you look at all these. Do we have an equation to, exactly calculate one? At least knock one of them out. And it's W, right? You look in the notes, and it was W was negative nRT natural log of V final or V initial or something. Right? Do we care about, volumes in liters? Do we need to get it to cubic meters? Right? Because cubic meters would be the standard metric units, so we can get joules and all this stuff. Do we need to do that? They're going to cancel out. You don't care what units volume is in, as long as they're the same. All right, so that's good. The little n, that was nice. The little n's going to be 1. What r are you going to pick? If you pick the 0.0821, what units would your work be in? Gosh, I don't think it's going to be calories even. See, the problem with picking the 0.0821 is you're in liter atmosphere per mole Kelvin. And that English system, man, I totally gave up on it a long time ago. I would knock points off if you gave your answer in calories, the British system. But I would use the joule one because it's so much more straightforward. So I would use the 8.314. So the work we have done, right? We can get an answer for it. Well, we probably should to help us out on the rest of this, right? So let's get an answer for it. Minus nRT natural log V2 over V1. All right, see if you can get an answer for it, and then we'll keep going. Yeah, temperature has to be in what units according to that R? Kelvin. Make sure that temperature's in Kelvin. Yeah. What did you get? Let's write it down. And then people can argue with you.
Awesome. Negative 1,574.12.
Yeah. Did anybody else get that? Kathleen, did you get that? You did? All right. So hopefully you're getting that for the work. Good. We got one of them. Okay. Okay, do we have any others we can get? Ooh, that's a good equation. That always works. That always works, right? Do you see how, when we're picking equations, do you see how this one does not always work? When would it not work? It's an equation, but it's not. Yeah, but it's not reversible. You can't use that. But this is a definition, man. This is totally how internal energy can change. Doesn't matter what the process is. It's always Q and W. It's the only way to change it.
We also use W as a negative external pressure times change in volume, or we not have to do that because it's constant pressure.
We know W. And we can't use W's minus P external delta V because that's a different process. That's irreversible. Anybody have an idea? A hint. Isothermal. What does that mean? Temperature's constant. So can delta U is internal energy, so it has to be what if it's isothermal? 0. Why? There's no change in temperature. The only way to change the internal energy is to change temperature, right? So that means delta U is 0. Did they ask for oh, they did ask for delta U. Okay. Delta U is OJ. Right? We have our W. We should put boxes around this. It makes it a lot easier to grade. Okay. Oh, now we should know Q. Q is going to be positive 1574. Okay, we're getting there. Delta H. Okay. Now what's an equation for enthalpy? Emily, what's an equation for enthalpy? Yeah, another definition. This always works. It always works. Okay. Now, but it's delta H. This is where you kind of just got to get used to playing with this. If you put delta H, put a delta in front of the H. Put a delta in front of the, so I don't skip any steps here, in front of this. Now it's plus. When you had two integrals, could you break, and you're adding stuff, could you break it up into two parts? Yeah. So because the change of something plus the change of something, or area plus area, whatever changes, you can add changes up. So I can distribute that little change, that delta U plus delta PV. Okay. Now, how pressure is changing and how volume is changing, right? What is PV equal to? nRT. This is the easy way to do it. It doesn't look easy, but it's going to be easy. Okay, so that R we can pull out, because that's not changing. Is N changing? They're not adding any gas. Is T changing? No. But if any of these were, you got to put that delta in front of it, right? But it's not. None of that stuff is changing. So this is 0. What's delta H have to be? Has to be delta U. Has to be OJ again. Yeah. Right? Okay. All right, now all that was for part A. Okay? All that was for part A. Now in part B, what changed? Against a constant external pressure equal to the final pressure of the gas. Okay. Expansion against constant external pressure equal to P final or something. I don't know. However you want. If you want to write out more, go write out more. Right? Is it still isothermal? Yeah, I should have wrote isothermal, right? What can we do? Any ideas? You do a P1 V1 thing? Oh. For what purpose? You're right, to get the final P, but why? Right? Have something guide your efforts, because you can just start doing stuff. But have a guide. In other words, what you're right, but there's a reason for looking for final pressure. Yeah, but you may not need it. What I'm getting at is, what equation do you have to use for work? It's hoping negative P EX delta V. Because the work is it still reversible? No, that's the only thing they really changed. So if it's not reversible, we don't have any other equation for work. That pressure has to be constant. Right? It has to expand against a constant pressure. Otherwise, we can't even use this thing. So that's what I guess I'm saying, Rob, is, and everybody, write out an equation first before it's not really random, but before you start putting your energies and efforts into stuff. Guide it. Get the equations down there first. In fact, before you even wrote this one, do the easiest ones first. It's isothermal. Delta U is 0. Right? If it says isothermal, man, right away. All right. Okay, so now well, it's kind of easy. It doesn't look like OJ. But how do you hear what Rob was saying about how to get that final pressure? Yeah, was it P1 V1 over T1 equals P2 V2 over T2, right? And if you're not sure, if you don't remember that, just remember PV equals nRT. So you divide both sides by nRT. All right, so this is where it's coming from. All right, just put 1s on it, it equals 1. Put 2s on it, well, it equals 1. So they equal each other. Okay. So we know, what can we cancel to get this P2? Well, how are we going to solve this? The T's are going to cancel because it's constant temperature. We know the volumes. Do we need to mess with their units? No, leave them alone. And don't we know what P1 is? Yeah, no, where is it? We don't know it. Uh-oh. Screwed? What's that? Use PV equals nRT and get it. Just put you can put little subscripts on everything, but some things it doesn't make sense to put subscripts on. It doesn't make sense to put subscripts on what in this? Well, yeah, because N never changes. Exactly. Or R. Yeah, and T too, because it's isothermal. In this case, yeah, so there it is. That's how you get your initial pressure. So we can get our final pressure. So then, so let's pretend you get your final pressure. Okay. And we got to put it in this equation. Concept review. We better have things in what units to get this to work. P has to be in pascals. That name of a cool kid. That and isosceles. I had to do all over again, it'd be Pascal and isosceles. Isn't that cool names? I think so. Anyway, delta V. That has to be in what units? Cubic meters. Right. What's the easy way to go from liters to cubic meters? 1 milliliters a cubic centimeter. That works. Or a liter's a cubic decimeter. So it'll work out either way. So we can get a number for W in joules. You get a number for W in joules. Done. So now what can we get? We're after Q and we're after delta H yet. How would you get the Q? W's done. How would you get the Q? This always works, exactly. That's not, notice there's a big difference between these two. Right? One works all the time. One doesn't. You got to be careful. Right? It always works. Okay, now we have Q. What's left is delta H. Play the same game we did before. Right? Now, does anything change? Does H come out to be a number this time? Or is it still 0? Can you see it? It's still 0. It's isothermal. So you can play the exact same game again. NRT. None of them are changing. So in other words, I think, isn't it safe to say, if it's isothermal, for sure what and what are always 0? Yeah. As long as they're not adding stuff. And they never do. Right? It's a sealed vessel. Otherwise, how could you even make changes? Oh, no, we're not done, are we? There's a C. Okay. Now we're in C. P external is 0. Now, is it still isothermal? Yeah. Isothermal, so what's all 0? Delta U, delta H. Yep, they're all 0. We still need a Q. We still need a W. So Amberly, what's up? How are you going to do this? We still need a Q and we still need a W. You hear what he's saying?
If your external pressure is 0, you're going to get 0 times.
Exactly. Let the equations guide you. This guy's 0. So he's 0. Well, if he's 0,
I love part C.
Q has to be 0. Right. It's isothermal. You got to keep the temperature constant. And there's nothing pushing up against it. It's a vacuum. It's not. It can't lose any energy. There can't be any change in internal energy. Okay. Okay. A sample of 2 moles of monatomic perfect gas. You're going to start seeing this a lot. The reason why they do this is because then you know what the molar heat capacity at constant volume is. Diatomic gas will be something else. But that's why they do this. It's initially at 1 atmosphere and 300 Kelvin. It's heated reversibly to 400 Kelvin at constant volume. calculate the final pressure, internal energy, Q and W. Now, why give us heat capacity? So what do you think? Now, there's a couple ways to think about this. I mean, you could just slap down an equation. It might help you. I mean, it looks like where would you go, where would you go, where would you go? But if it's heated reversibly, what's the equation for work you're supposed to use? W is negative nRT. Okay. So what did they say regarding nRT, well, NT or the volumes? Volume's constant. Well, if volume's constant, what does that do to that equation? You're going to be taking the natural log of what then? 0. It's going to be volume's constant. It's always 1, right? Because whatever you're going to put in there for volume, who cares? It's going to cancel. Because V2 equals V1. What's the natural log of 1? 0. All right? Prove it to yourself, Alice. Isn't it 1? Yeah. Okay. So this is 0. Okay. Now they gave us, we still need Q, and we still need delta U. Someone said something. I think I. All right. Skim back here. Why? It would. I think you're looking at this. Is this what you're thinking? If W is 0, she's saying if W is 0, Q has to be 0. Yes, if this guy's 0. But is all I got to look at, is the temperature changing? Yeah, so this definitely is not 0. So that means there must be another way to get it. I mean, this always works to get delta U, but we're missing what the Q is. There must be another way to get delta U. And it only works under certain conditions. It's going to be a special equation. Yeah, Emily, keep going. The heat capacity. Okay, what's the what's the relationship for it? All right, go back in the notes. Well, we don't want to mess with enthalpy. That's throwing a whole other thing in there. All right. Go back. Let me give you I'll just find it in here. It'd be easier than trying to.
Looking at our equation sheet.
Yeah, here's one. Yeah, here's even better. But it's not staring at you in the face. Right? If you did integrate, right, you'd have delta U equals CV delta T, right? Delta U equals QV. Q is really just, it's kind of here, CV delta T, right? If you know what the heat capacity is, you multiply it times the change in temperature. No matter how complicated and ugly the system is, if you know what the heat capacity is, you know what the temperature changed, just multiply the two, and that's how you get the heat. It could have been water, it could have been anything. But if you ever know the heat capacity, you multiply it by the change in temperature, and you get the amount of heat. It's just that you have to use special heat capacities if it's under special conditions. Here the volume didn't change, so you better use the right heat capacity. You better use the CV, because that's for constant volume. Because it's going to be different for constant pressure. It'll be a whole different number. So Q would, if you'd like to write an equation, it could be like Q equals C delta T, right? And you can plug in the right C that you want, right? If it's constant volume, you put a, is there? Oh, there. No, shoot, there it is.
Right here, right in
Right?
the middle of the page.
But help yourself out. In other words, you know what's coming up, the exam. What is given on the exam,
That's what I was
right?
thinking.
Okay. Oh, there it is. Calorimetry. Q equals C delta T. Right? Yeah. I guess we should have jumped right to that instead of only going back to the notes. Okay. So we've got our Q. Farther. We know what our change in temperatures. We're good. So how are you going to get the delta U? Yeah. Delta U is equal to Q. This always works. Definition. Always works. So I guess the message I'm trying to send is some equations don't always work. Right? It depends on what's going on in the process. It doesn't always work. Okay. About a minute left. Okay. Since we have about a minute left, we have the same sort of stuff. How about, are there questions on the exam that you got back? Right? Because the final exam, it's not going to be identical to these hourly exams, but I'm going to take questions off of there. So you want to make sure that you got, if you haven't picked it up yet, pick it up. What's that? You don't have your exam in your folder? Maybe it's in your... There, that's why. You're what do you call those spies that are in more than one double agent? So if you have any questions on it, we have a couple minutes, right? A common mistake was using the wrong R on some question.